Okay. Um, yeah. So today, so today's lecture 11, right, or actually week 11 of the course, and this is going to be the last kind of lecture in this way, because the next 3 weeks are going to be the presentations by the students. So today we are going to talk about actually applications of optimization, right? So I think like that, like last 10 lectures we looked at the optimization problems and also like algorithms, right? So we looked at continuous optimization at one end, and we looked at discrete optimization, and then we looked at different flavors of optimization, right? In continuous optimization, we looked at um, kind of various kinds of problems, like strongly convex, non-convex, smooth, non-differentiable convex functions, basically Lipschitz continuous functions, and so on and so forth, right? We also looked at various scenarios like constraints, right? So we looked at constraint problems, unconstrained problems. We looked at algorithms for constraints, right? Then we looked at different flavors of algorithms. So we looked at first order methods, like gradient based methods. We looked at second order methods, like basically uh, quasi-Newton algorithms, right? Like LBFGS, BFGS, etc. We looked at first order methods which have like a second order like flavor, like conjugate gradient and Barzilai-Borwin gradient descent, right? So we studied a rich class of algorithms in the continuous optimization space. And then we looked at now discrete optimization, particularly we looked at submodular optimization, and we saw different flavors of submodular optimization, right? So we saw submodular minimization, we saw submodular maximization, we saw different kinds of submodular optimization, like, for different kinds of submodular functions, like, monotone submodular functions, non-monotone functions, sometimes even non-submodular functions, right? And we looked at different kinds of constraints. So we looked at unconstrained submodular maximization or minimization. We looked at cardinality constraints, knapsack constraints, matroid constraints, and so on and so forth, right? We looked at different settings. So we looked at streaming setting, distributed settings, online settings, and things like that. So essentially, we covered an entire gambit of optimization algorithms. A lot of it was focused on the theoretical part and algorithmic part, right? Try to understand, do these algorithms work? When do they work? What are the convergence bounds they have? What are the approximation guarantees they have? So now in this lecture, right, I'll actually talk about several applications of optimization, right? So I'll actually hopefully try to at least give a basic idea of what where kind of optimization comes up in machine learning, right? Since this course is, I mean, advanced topics of optimization in machine learning, I'll be focusing on applications in machine learning, right? So I'm not really going to be talking about applications in other domains as much, mainly because just I don't have the expertise, to talk about the other domains. But I know a little bit about machine learning, so I'll try to cover some of the flavors of optimization problems in machine learning. So the first part, I mean, typically people don't do it this way, but I thought, I thought of giving a flavor of the different optimization algorithms and kind of viewing these problems from an optimization and a loss function lens, right? I think it's super critical to view machine learning from that lens, because like the way I always talk about in my machine learning course, right? When I cover this in machine learning, I always say that there are really two pillars of machine learning, right? So machine learning is like the entire foundation, right? Um, and there are really two main pillars of machine learning, right? So the first pillar is essentially um, optimization, and the second pillar is statistics, right? And finally, you have like your foundation, which basically even like all of these kind of rely upon, and a lot of this is like like calculus, probability, and basically um, like matrix algebra, so on and so forth, right? So this is the way like kind of I like to view machine learning, right? And one important pillar here is definitely optimization. And the reason why optimization is an important pillar is because there are like both continuous and discrete flavors of optimization that come up, right? And these optimization problems typically appear a lot in various kinds of machine learning, and I'll give you a flavor of why and where they appear. Okay, so continuous optimization most notably comes up in viewing loss functions in machine learning, right? And various kinds of loss functions in various learning scenarios. So I will actually cover a little bit about that. And discrete optimization typically comes up in either like auxiliary problems, right? So here a lot of this is like loss functions in ML, right? And a lot of this over here is actually like, you know, auxiliary problems or like inference problems. And I'll actually talk about what I mean over here, right? So a lot of the continuous optimization happens in learning. So this is the learning step, right? Um, and this typically happens in the inference step. So this is the way, you know, how basically optimization comes up, and we kind of do a deeper dive now a little bit, right? So let me know if there are any questions. A lot of this will be clear to a lot of you guys because, you know, you have taken a machine learning course and you know the basics of machine learning, but I think still it's kind of a good recap, right? So in machine learning, there are different ways you can define a loss function depending on the task that you have, right? So broadly speaking, you have like machine learning as an umbrella term over here, right? But within machine learning, um, sorry. So within machine learning, you have like different kinds of machine learning, right? So you have like at one end, you have the supervised learning, right? Then in between, you have things like, you know, semi-supervised, you know, you have like um, online learning, you have active learning, right? And then you have like unsupervised, or like recently, what is also known as like self-supervised. And basically, these are just different flavors of learning in different settings, right? So in the supervised learning setting, you assume that you have access to, you know, xi yi pairs, right? So you have like the entire set labeled, right? Whereas so basically this is entirely labeled, right? Whereas in semi-supervised learning, you have like some examples which have labels, right? And some examples which, so it's basically labeled plus unlabeled, right? So you have some examples which are labeled and some examples which are only labeled, right? I mean, which are completely unlabeled, and you want to use both in the learning, right? And I think active learning also has a similar flavor, just that in active learning, you are like actively kind of selecting points to label. So we'll actually look at some of this, the optimization problems involved in active learning in a little bit. Online learning is like a continuous learning scenario where you have data coming in a stream, right? So here in the online learning, you have data coming in a stream or like continuously, right? So it's also called continuous learning these days. So there is like a new avatar of kind of online learning, which is gaining a lot of significance these days in machine learning. in the last 1 or 2 years, which is continuous learning, right, or continual learning. Then there's the other extreme, which is unsupervised learning, right, where you have everything which is unlabeled, right? And here you either want to learn clusters with either like some kind of a clustering task, right? Or it is a representation learning task. So what I mean by representation learning is that you're trying to learn features, right? Now, each of these problems, okay, so actually there are many more problems as well. There is like, generative modeling over here, generative adversarial networks. There is like robust learning. There is, meta learning, and so on and so forth. Right? So there are actually many. So there's also reinforcement learning, obviously, which I didn't even cover here. So a lot of these different kind of types of learning problems come up, and a lot of this depends on the scenario you have at hand, right? So I'll just kind of write this down over here that there are other forms like reinforcement learning. There is meta learning. There's multitask learning, and so on and so forth. Right. So there are actually several other forms of learning, and each of them have a kind of slight different twist. But at the end of the day, right? At the end of the day, any of these tasks. So there's like in some sense an underlying mechanism, right? And this underlying mechanism would be would basically involve the following steps, right? So essentially, you try to formulate your setting, the problem or setting that you have, right? And secondly, come up with a loss function that makes sense for your setting, right? So once you come up with a loss function that makes sense for your setting, then the third is understand or try to optimize this loss function. Right? And this would invariably, almost always, involve some form of a continuous optimization. Right? So we'll talk about where discrete optimization comes up, but right now we'll focus on continuous optimization. Right? So this is the recipe, right, of almost all machine learning problems, including like variants of deep learning. Right? So obviously now when you talk about coming up with a loss function, there's like some kind of implicit step over here that you also need to come up with a model, right? Come up with a model for the task, right? So essentially, there are two things over here, right? So the model that you care about is essentially kind of learning a hypothesis function, right? So the first is model, right? And this is you want to learn a hypothesis function, right? Which is basically h or h theta of x, right? So theta are your parameters, right? And this hypothesis function is going to be the thing that you're going to predict, right? So depending on the setting, it could be, say classification where you're predicting one of k classes. It could be regression where you're predicting, continuous value output. It could be like reinforcement learning where you're predicting an action, right? And so on and so forth, right? So depending on the type of machine learning, it could be a ranking problem where you're predicting a kind of ranking output, right? So different flavors here have different outputs, right? But at the end of the day, you want to learn a hypothesis function h theta x, right? So this is what is your model. So your model is this hypothesis function that takes in your input x, which is basically an input domain, Could be an image, it could be a speech signal, it could be natural text, or it could be just tabular data that you have, right? Could be customer records, for example, if you're trying to predict like certain customer behavior, or churn prediction or something like that, right? Or fraud detection. All of these in machine learning, you have your hypothesis function. I cover a lot of this in my machine learning course as well in the first 2 lectures, but I'm also giving a flavor here because I'm connecting optimization now, right? So now the second part is which is kind of equally important, right? Is the loss function. And the loss function here is where we basically want to design a loss L of h theta of x, right? So this loss could be, some kind of a supervised loss where it is like a loss function between h theta of x comma y, right? So this is like supervised, right? Or it could be unsupervised where you just have h theta of x, right? And obviously, I mean, is like you may ask that, like what's going on in the unsupervised loss, right? I'll actually discuss some intuitions that people have come up in designing unsupervised losses, and we'll talk about that a little bit, right? But basically, these are the 2 main flavors of loss functions, right? And this loss function now, depending on how you design your loss function, it could have certain properties, right, that you care about from your learning perspective, right? And also it could have certain properties from optimization, right? So once you have A and B done, then you can do step number 3, right? So in some sense, this is in step 2, where this is like, so maybe I'll call this like 2A and 2B, right? So this is part of 2, because in 2 you want to come up with a model and you want to come up with your loss function, right? So this is the underlying mechanism of loss functions in machine learning. Now, what I'll do is I'll actually talk about a few different scenarios. It's not exhaustive by any means. I just put this up last night, so I'll talk about a few example things in machine learning of how you design these loss functions, and then I'll talk about what the optimization is. So I won't talk about optimization algorithms because most often they would use one of the flavors that we have looked at in the past, right? And most of this comes up in the deep learning literature. So very often it would be using a variant of deep learning, but you could also do this in the standard learning scenario as well. And in that case, then you would use some form of a convex optimization algorithm, right? If it's like a standard single layer model like a logistic regression or something. Any questions so far on this? Okay. All right. So let us talk about now the supervised learning setting, right? So supervised learning setting is where you have your data, which is basically x1, y1 until xn, yn, right? So everything is labeled over here. So yi's could either be a discrete one in k, right? Which is like basically which is classification. If k is equal to 2, then it's binary classification. If k is greater than 2, then it's multi-class classification, right? Or this could be continuous, right? And basically it's like y in r, right? And this is in the case of regression, right? So now given this, like as I said, right, you have your loss function now, right? And your loss function L is basically going to take your hypothesis function h theta of x, right? And it's going to compare it to y, right? And essentially the idea now is that my h theta of x is going to be my prediction for an instance x, right? And y is the true label. And what this loss function tries to say is that if the two are close in some sense, right? then it should have a small loss, right? And if it is, if the two are far away from each other or they're completely different, then it should have a larger loss, right? And depending on classification and regression, you have different kinds of loss functions, right? So that's the basic idea of a loss function. And the optimization problem would be where you try to minimize on your training set, right? So you take I from 1 to n, and you are taking your loss function of h theta of xi comma yi, right? So this is what your loss function is. So you're taking your training data set, and you're taking the sum of the loss function in your training data set and trying to find the theta which minimizes this sum of losses, right? So this is the supervised learning perspective over here. And the entire magic of supervised learning is designing this loss function, right? So that's where in the machine learning class we spent several lectures, right, talking about different kinds of loss functions. So just a very quick primer, right, of what are the kinds of loss functions. So in the case of classification, right, in the case of classification, what you really care about is you care about you care about y multiplied by h theta of x, right? And the reason is because your y, right? So for example, we'll kind of take binary classification for simplicity, right? I mean, a similar intuition holds for multi-class as well, but in multi-class, typically we consider y to be a vector, kind of a one hot vector, right? So for simplicity, let's just talk about binary classification, and the same intuition can extend to multi-class as well, right? So now in the case of binary classification, you have your y to be either +1 or -1, right? And your h theta of x is typically a probability or something like that, right? So it's a prediction of what your model's output is for a given x, right? So if your h theta of x is greater than 0, that means that you're predicting it to be a positive, right? And if it's less than 0, you're predicting it to be a negative. So because you're multiplying y and h theta of x, if this multiplication between the two is greater than 0, what it means is that the sign of y and the sign of h theta of x match, right? So both of them are in the same direction, right? So if they are positive this side, right, what we really want from our loss function is we want it to have a small loss, right? So we want the loss function here to be small if they both have the same sign. But if they have a sign which is opposite of each other, right, then we want the loss function to be large. Why do we want it to be large? Because they are contradicting each other, right? So somehow h theta of x is not able to predict the same sign as what y is. The reason is because in classification, we will actually oftentimes use sign of h theta of x to be the final prediction in binary classification, right? So that's the intuition of loss functions. And different loss functions, like logistic loss, for example, right? So this is a misclassification loss, which is 1, 0, right? So if you are misclassified, you have a loss of 1, otherwise you have a loss of 0, right? Then these are different examples of loss functions. So this is what is known as a support vector loss, which is also a hinge loss, right? This is a sigmoid, right? A sigmoid looks like this, the pink one. Then you have many other loss functions, right? You also have a logistic loss, which is not in this figure, but you have a logistic loss, and so on and so forth. So you have different loss functions here. These are examples of loss functions used in classification, right? Logistic loss, log loss, focal loss, scale divergence, exponential loss, hinge loss, right? Hinge loss is the support vector loss. By the way, there is this nice Medium article. There are actually several of these which will explain to you what a loss function is. I've taken this. Many of these images come from this particular Medium article, right? The goal of regression is slightly different, right? In the case of regression, you want to somehow have a difference. So you have like some kind of a function on the difference between y and h theta of x, right? And typically you want your function to be some kind of a positive power function, right? So for example, with a square loss, this is how a square loss looks like, which is a mean square loss, right? If you take a L1 loss, your L1 loss, which is the MAE over here, right? I think the MA is like the minimum average or the max average estimate. I forget what, or sorry, the mean average estimate, right? So this is the L1 norm, right? And then you have different versions. You have the Huber loss over here. You have the quantile loss. So you have different kinds of regression losses. All of them do things slightly differently, right? And they're all useful for different purposes. Some of them, the way they treat outliers is different. They are more robust to outliers. Some are less robust to outliers, and so on and so forth, right? So depending on what your application is, you will come up with different loss functions. Now these loss functions will all change properties of the optimization algorithm inherently, right? Because your optimization algorithm will probably depend on your loss function. So your loss function may have certain properties like strong convexity, it may be Lipschitz continuous, or it may be non-differentiable, so on and so forth, right? So you will have all of this would depend on your loss function in turn. Okay, so this is supervised learning, right? A very quick summary of supervised learning. We have unsupervised learning. One standard example of unsupervised learning is clustering, right? In clustering, what basically goes on in clustering is that you want to essentially you have your data points. Your data points are essentially just your features, right? So you have just I from 1 to n, right? So there are no labels, right? And the goal over here is to somehow partition your data into k bits, right? So this is the goal of clustering. So imagine that you don't, so imagine that you know that there are like two classes, right? But you don't have any labels for your classes, right? Then what can you do? Well, what clustering will try to say is that it will say that points that are close by to each other should basically belong to the same class, right? So you'll try to get a decision boundary that looks something like this for your task. Now, unfortunately, because you don't have any class information, right? You don't really know whether your decision boundary is going to look like this or is going to look like this. Right? All you know is that points that are close by should be clustered together, right? But obviously there will be points that are close by like this towards the decision boundary that would still be close by, but we still need to draw a boundary, right? So that's one problem of completely unsupervised learning, that if you try to come up with a decision boundary based on your kind of clustering, there can be many optimal clusterings, right? And all of them are optimal from the sense of what clustering cares about, but they may not be optimal from the end task in mind, which is predicting predicting something, right? Then your clustering may not be a right fit, but at least it is doing something, because it is kind of merging points that are like close by to each other. So these are two example objectives for clustering. So again, this is a loss function. A loss function here, it is trying to come up with some form of like centroids, right? So the loss function here involves finding centroids. Another way of viewing this is from a discrete perspective, where you want to partition your space into two groups, right? So you can view clustering either as a discrete problem or as a continuous problem, or as both, right? You can view it as a continuous problem by finding the continuous centroids, right? The centroids, and optimizing this. So this is the continuous loss function here. And a discrete loss function involves finding a set of points, or basically finding a partition, right? So finding a partition C1 and C2 such that C1 union C2 is equal to the entire set. Okay. Now, for the loss function f of c, you can have multiple clusterings, right? And the loss function will look something like this. So there's a region here where there are multiple good clusterings, but there are really two optimal clusterings here, right? And C1 and C2 are these two extremes. One is you cut it this way, and the other is where you cut it this way. And both of these are good clusterings. But if you do any other clustering, then it's not as good, right? So this is the insight of clustering. Okay, so there's one more thing I want to talk about. I don't have a slide for that, but I'll talk about. This is related to this is something that is kind of gaining a lot of significance these days, which is self-supervised learning. right? So this is another form of unsupervised learning. And in self-supervised learning, what's going on is that the goal is in self-supervised learning is to learn a feature representation, right? So self-supervised learning is not trying to, or maybe I'll just call this h theta, right? So the goal of self-supervised learning is not to finally learn a classification task, right? Because we don't have a classification task at hand. We don't know what we're going to predict, where we're going to use this model for. But what we do know is that we want to have a good kind of a representation of my data points, right? So given my features X, which could be an image, I want to be able to learn a good feature representation. I want to kind of do a representation learning so that images which are close by should ideally be close in the feature space, right? And similarly, images which are like different, very different from each other, should be far away from a representation space, like, right? And the idea is that once I have a good representation, then I can actually do some very simple transfer learning on this to actually learn it on my given task at hand, right? So that's where a lot of self-supervised learning and unsupervised learning comes in. This is gaining a lot of prominence these days in computer vision and um, in natural language processing, right? In fact, a lot of language models these days, like I don't know if a lot of you have heard about things like GPT-3 and BERT, etc. All of these are like unsupervised learned models, right? Basically language models. And all they're trying to learn is like that whether words are similar to each other or not, right? And whether, images are similar to each other or not. The basic idea of this is that you take an image X, right, and you pass this to your deep model or your feature representation model, which is h theta, and then you take your X prime, and your X and X prime are basically like maybe some augmentations of each other, right? And what I mean by augmentations is that they are like maybe perturbations of each other. So they could be either like maybe you add some random perturbation to X and you get X prime, right? Or they could be like some rotations of X, right? So basically by augmentations, you could have like perturbations, or it could be like like random flips or flips. For example, like horizontal flips, right? And you could also like crop the image randomly, right? And so on and so forth. We have multiple kinds of augmentations over here. So X prime is like the augmented version, right? And basically what this is saying is that you pass X and X prime to H theta, and the output of this, right? So you take a loss function now, which compares basically H theta of X and H theta of X prime, right? And this loss should be small. So now you can, given your completely unlabeled data set, right, you can pose a problem as minimizing theta of sum of I from 1 to n of some loss function of like h theta of x and h theta of x prime, right? Of course, this is a very, very simple kind of idea I'm putting here. Obviously, many versions of self-supervised learning algorithms are there. In fact, in many universities, you have an entire course on self-supervised learning, right? A special topics course. So by no means I can cover this in 5 minutes. But this is just one way of doing self-supervised learning. But the basic idea is the same, that you are trying to take two images which should be very similar to each other, or like two words which should be very similar to each other, and try to enforce through your loss function that they should be similar, right? And you learn your model. Yes, Luai.
So what would we benefit here when we introduce a perturbated image?
Mm-hmm.
What gain do we get from here? Yeah, shouldn't this be minimal in the first place, because we just added some very, very small features to the feature vector?
Yes. Yes. So the whole point is that once you do your augmentation, so once you do a perturbation, or once you do a random crop or a flip or whatever, right? Then your loss, so based on your loss function, right, the two should not change significantly, right? So both of these should ideally be very close to each other. So this is what you want to enforce, basically, right? So you want to enforce that. So for example, you want to minimize, like one way of a loss function is to minimize the Euclidean distance between s theta of x and s theta of x prime. Right? In fact, we'll talk about some of this in semi-supervised learning as well, because similar ideas are used in semi-supervised learning. So essentially the goal here, Luai, is that once I feed my x into this model, this is a deep model, right? And I get a feature vector. So as well as a question, Saurabh, a related question, is s theta a distance metric? No, s theta is not a distance metric. S theta takes in my image and outputs a vector, right? It could be an n-dimensional vector. So it's a deep model. It's parameterized by theta, but it's a deep model. It outputs a vector, and it's a representation, right? And the idea is that once I take my representation, I want to make sure that my representation is consistent across augmentations, right? So suppose I take an image of a dog and I want to vertically flip it, right? Or I want to like crop it randomly. I mean, not crop it too small, but like basically remove like say 10% of the image by randomly cropping. Very likely there would still be a dog in it, right? And even though it's like a cropped dog, the model should still predict it's a dog, right? So that's the intuition of self-supervised learning. In the case of natural language processing, things are a little bit more fancy. There you want to use like sentences, and you want to say that words that appear together in a sentence are like somehow related, right? And you want to kind of learn this in your representation function, that these words are related, right? So you have a very large corpus of text, and you want to ensure that words that appear together in this large corpus of text are related, right? So that's the basic idea. Does it make sense? So basically, the whole point, or the takeaway here, essentially, right, is that you can pose a lot of this as continuous optimization problems as well. And a lot of this the magic here comes in designing the loss functions, designing these networks, and exactly coming up with this. This is just one example of doing self-supervised learning. Yeah, Harsha.
Professor, I was just wondering, how would the self-supervised learning perturbations and augmentation work in case of like tabular data, which we usually have in machine learning?
That's a good question. I think I'm not sure of work in self-supervised learning. Yeah, so I think Krishateja is saying you can do noise. So I don't know of papers that have looked at this for tabular data. But yeah, I think that there are approaches where you can add some noise and make sure that your features don't change too much, right? Your decision space remains the same. Yeah. Does it make sense?
Yes, thank you.
Okay, awesome. So now I'll talk a little bit about semi-supervised learning. So it's kind of related to the self-supervised learning space, except that here in semi-supervised learning, we have like two sets, right? So we have the set D, right, in this equation, which comprises of xi, yi pairs, right? So this is the set D. So this is basically labeled, right? And then I have the unlabeled set, which is just xi in U, right? And this is unlabeled. Okay. So there are two components in the SSL loss function. One component is like the supervised component, right? And the second component is on the unlabeled data or the unsupervised, right? This is on the labeled data, unsupervised. Okay. So essentially the basic ideas over here are very similar to, again, the self-supervised learning, right? So you have your loss function L, which is the same, right? So imagine you have your data set like this. This is basically the 2 moons data set, right? So you literally take like 3 points over here to be your positive class and 3 points to be your negative class, right? And if you just use supervised learning, right? So this is the supervised learning. It would cut it something like this, right? So obviously it is making a lot of errors here, because ideally speaking, in your two moons data set, this is really a different class. These two, right? Where it is kind of making errors over here, right? So are you able to see the image clearly? Right? So this portion is entirely wrong, right? This portion also is wrong based on a supervised decision boundary. So what we really want is a decision boundary that looks like this. So it turns out that there are some very simple approaches for semi-supervised learning. You can just do pseudo labeling, right? So pseudo labeling means you take your supervised model and then you just apply your pseudo label to your x, right? And essentially your f of xj comma theta is going to be nothing but you're going to, so in pseudo labeling what you're going to do is you're going to take your L, your same supervised loss function, you have your f of xi comma theta, right? And here you apply your y hat to be the hypothesized labels, right? So this is your nothing but your f of xi comma theta hat, right? Where theta hat is the model trained on the labeled set. What is pseudo labeling? So that's what I'm describing actually, Luai. So pseudo labeling is where I'm taking my, so theta hat is the model that is trained on my labeled set, right? So given these three examples, I train a model. This is my supervised model, right? What this will do then is that this will apply the prediction of this model to these points, right? So basically everything over here in this part would be labeled black circle, right? Everything over here would be labeled a white circle, right? And I basically then use my hypothesized labels and basically combine this. So essentially I'm making a much larger labeled set which contains the labeled set here plus the hypothesized unlabeled set, right? And I train a joint model. So I do supervised learning on this entire set. So as you can see, pseudo labeling does very poorly, right? And it's not surprising that it does very poorly because the biases are reinforced, right? My pseudo label is noisy, right? My hypothesized labels are noisy, and I am basically reinforcing my hypothesized labels over here to try to get the prediction. Does it make sense, Luai? Okay. There are also other techniques like entropy minimization. This regularization is entropy. That also does not actually oftentimes work very well. There are some very recent deep learning based algorithms. Things like consistency regularization, pi model, mean teacher, VAT, mixed match, fixed match, etc. These are all very, very recent techniques. I think some of you are going to be covering semi-supervised learning actually. So you'll get more details over there. I'll just talk about consistency regularization because it's very related to this self-supervised learning. So the basic intuition of many of these algorithms is exactly the same, right? They apply they take these points and then they will apply some augmentations to it, right? Or they will apply some perturbations to it. And what the regularization will enforce is that once you apply perturbations, it should belong to the same class, right? And this very simple regularization will ensure that actually the decision boundary moves something like this, right? So interestingly, if you were to do a clustering, just a self-supervised learning with this, right? You would end up getting actually something pretty good. I don't know exactly of self-supervised learning in this scenario, but my hunch is that you would get something very reasonable because of this very rich consistency regularization that is being enforced, right? So consistency regularization is exactly this idea over here, that you do some kind of augmentations or you do some kind of some kind of a perturbation, right? And you enforce that the predictions are consistent across them, right? And you additionally add this to your labeled set. So you combine, you do a combination of this. So you have your labeled loss and you have your consistency regularized loss on your unlabeled set, right? And this, for example, the VAT, right, magically just with 6 labeled points on the 2 moons data set is able to retrieve this kind of more complex decision boundary, right? So a lot of this has been done in the last 2-3 years, maybe 4 years in the deep learning, machine learning community. And this has proven to be very, very successful and very powerful actually in deep learning, right? To learn with very, very few labeled data points. So I think this is, in my opinion, very exciting because this is solving a very important problem of trying to do powerful, machine learning with very few labeled data points, right? Okay, so now I'll talk about a few other flavors very quickly. Again, I was hoping that this would be very quick, but I ended up spending a lot of time actually in the first few slides. But anyway, I'll be very quick over here, right? So meta learning is this flavor where it talks about like learning or adaptation, right? So the idea is that you have what is known as a meta training set of tasks, right? And they are basically a set of tasks that you want to train upon, right? That you want to initialize essentially your models, and your meta testing is basically your deployment tasks, right? So the idea in meta training is that I want to create a good initialization from my meta training set, so that once I fine tune on my meta testing, which is very few data points, right? I want to perform really well, right? So this is really critical in a few short learning scenarios. So a few short learning is a scenario where you have multiple tasks, right? Each task. So imagine you have like a problem of predicting like cancerous images in medical image data, right? And you have various X-rays and CT scans. Now you have many similar tasks, right? And you have many similar images, but each task has very few images. So you have like say 10 images, 10 labeled images from each task, right? And a task could be, say, one task could be predicting breast cancer, another task could be predicting breast cancer from certain slightly different kinds of images, right? Another could be predicting like maybe lung cancer, right? So you have different kinds of these tasks, and you want to somehow learn from kind of jointly from all of these tasks, so that you have a good initialization, so that finally in my deployment, if I have very few images of a particular meta testing scenario, I want to perform well, right? So the main idea of MAML, which is model agnostic learning, is that I want to take like say one gradient step in each of these meta training tasks, right? And after taking one gradient step, so this is my loss that takes one gradient step, right? So after taking one gradient step, I want to make sure that my model initialization is good. Okay, so this is related to what we will see a little bit later, which is called bi-level optimization, right? And the basic idea is that given my theta, I create a theta prime, which is theta minus this one gradient step on my task tau I, right? So this theta I itself is a function of theta, right? So essentially now I have my loss function here, and my loss function now consists of these L of theta I prime of theta, right? So finally, this is a loss function in theta, but it's a bi-level loss function, right? Because each of these inner theta I prime itself involve like an optimization problem. And in fact, you can do like one gradient step over here and you can solve this. So MAML actually was introduced in this 2017 paper by Chelsea Finn and others, right? And essentially, this has actually kind of turned out to be very powerful in several problem scenarios, right? In fact, it's a very nice approach to solve bi-level optimization, which we'll take a look at, right? But meta learning itself is this scenario where you want to do augmentation. Oh, sorry, you want to do domain adaptations in a few short learning problem, right? And again, this is posed as an optimization problem, and you can solve this optimization problem, right? All of this. So model agnostic meta learning basically is like a gradient based approach, gradient based learning approach, right? So again, this is the algorithm of MAML. I won't actually spend a lot of time here, but it just suffices to say that you essentially want to take your inner gradient steps, right, and finally you take your outer gradient steps, which inherently depend on this inner gradient step over here. Okay, so now we'll switch gears a little bit and we'll talk about min-max optimization, right, and particularly we'll talk about GANs. So before this, I'll talk about the motivation of GANs. So GANs are basically comprise, and it's basically called generative adversarial networks, right? And the basic idea of GANs is that you have your generator, right, which generates images. So given some random noise, you generate fake images, right? And then you actually take your real images from a training set. So all of these are basically unlabeled actually. So this is like unlabeled images, right? And all your discriminator is doing is that it is actually taking these kind of fake generator images, so fake images, and it is taking your real images, right? And it is trying to predict whether this is real or fake, right? That's what your discriminator is doing. And the whole idea of GANs is in an adversarial manner to try to jointly train your generator and discriminator, right? So you want to train your generator so that you can try to fool the discriminator, right? And you want to train your discriminator in a way so that you can basically not be fooled by your generator, right? So yeah, so GANs actually have had multiple applications. I think the most important of them is to actually generate images, right? And it's one of the first kind of strategies where you can generate very realistic images. In fact, generate even videos. So a lot of the deep fakes that you hear about, right? You have a video of Obama, for example, right? And Obama is saying something that you want Obama to say. And in fact, this can be very harmful potentially from a societal perspective. But anyways, that's something that has actually gained a lot of traction today. There was this video of Tom Cruise, for example, talking something, right? And this was completely a fake video created by something like this, right? So basically the point is that today you can actually create a lot of, this technology has actually adapted a lot since the original 2014 paper. So this was actually introduced by Ian Goodfellow. I'm sure most of you know about Ian Goodfellow in 2014. It's a NIPS 2014 paper. So it's already 7 years back, right? But I think the field has exploded in the last 7 years. So this is an example, right, of one paper which has created an entire field of generative adversarial networks now, and there are probably almost tens of thousands of papers that have been spawned from this one paper by Ian Goodfellow, right? So he invented GANs, literally speaking. Anyways, so the basic idea of GANs is that you have some latent space, which is basically noise, right? And you take a generator, and then you generate like fake samples here, and then you have some real samples, and you have your discriminator, and you want to basically, your discriminator says whether is this like real or fake, right? And you want to kind of feed this back into the generator and your discriminator, and you want to learn, right? The basic idea is that it's min-max. The reason it's min-max is because your generator wants to minimize this loss function, right? So your generator wants to basically generate images which can fool the discriminator, right? And your discriminator wants to basically distinguish between them, right? So you minimize your generator, you maximize your discriminator of this LDG, right? So your D is your parameters. So these are your D parameters, right? And your G here is your generator parameters, right? And this is an example of a loss function here. So you have a log of D of X, right? And what this loss function basically saying is that you have your expected loss on your discriminator, right? And then you take your log of 1 minus D of G of X, right? So this is the output of the generator, right? And what we are basically saying is that the discriminator, the D of X and the D of G of X, right? Both of them should be basically so this is the loss function that compares the two, right? What the generator is trying to do is it's trying to minimize this loss function. What a discriminator is trying to do is it's trying to maximize this, right? And they are basically doing this in a game theoretic manner, in a min-max game theoretic manner, basically. And what is interesting is that you can actually show with this loss function that if you take the optimal discriminator, right? So you just maximize the inner. So for a given generator, you take the max D, you basically maximize this and take D star, which is the maximum of this, right? This quantity is nothing but 2 times the Jensen Shannon divergence. I'm not defining this. It turns out that this is the symmetric KL divergence, right, between two distributions. So the Jensen Shannon divergence between these two distributions, which is the real distribution PR and the generated distribution PG, right? What it's saying is that at the optimal discriminator, right, this will really be the divergence between them. So if you minimize this quantity, what you're trying to minimize is that you're trying to achieve PR to be equivalent to PG, right? So you're trying to achieve a generator which can exactly match your real world distribution, right? And it can start generating objects in this real world distribution. So this is a very powerful result, right? Because what this says is that if I can optimize this exactly, it will really give me what I care about, right? It will give me a generator which is going to generate something that is very realistic, right? So a lot of machinery now has actually gone in the optimization literature so that we can actually optimize this loss function exactly. We have not covered min-max optimization, right? But it turns out that this is actually solved again in a joint gradient descent manner, right? So you do gradient descent for certain epochs and you do gradient descent for certain epochs, and you jointly do this. Okay, so this is GANs. Again, this is the algorithm for GANs. This is what I talked to you about, right? So you update this by ascending. So you ascend in a stochastic gradient descent manner on the discriminator. So you maximize. So recall that your discriminator is maximized, right? So you're doing stochastic gradient ascent, right? And then over here you are doing actually stochastic gradient descent on your generator. So you're doing ascent on your discriminator and you're doing descent on your generator. And that's why it's a min-max. You're increasing one while you're decreasing the other, and finally you will reach some kind of a Nash equilibrium. So it's really a game theoretic kind of setting, right? And again, there are like tens of thousands of papers actually on just GANs now in the last 7 years. So it's incredible. It's an incredible space, very exciting space. Again, which has a lot of optimization in it, right? Okay, let's look at another adversarial. Yeah, Luai.
But this one, I believe, is more robust and powerful in computer vision as opposed to cybersecurity, for example.
Which one? Sorry.
Computer vision as opposed to cybersecurity.
So what is more in computer vision? Can you
the GAN is more.
Yeah, so GANs, you're right. So GANs mostly have been used for images. I think I don't know about use of GANs for other forms of data like text, etc. Actually, does anyone know?
I've read a paper about this, and they used something else for cybersecurity. They compared it with GAN, and it performed much better than GAN.
Okay, yeah, so it's possible. So I think GANs, the goal of GAN is to generate things, right? It's doing it in an adversarial manner, in this game theoretic min-max manner, but it is really, the goal is to be able to generate things. So the goal is not robustness as such, adversarial robustness. In fact, we'll talk about adversarial robustness now, which is very relevant in the cybersecurity world. And there are slightly different approaches here. Is the Jensen-Shannon divergence hard to optimize? Not really. Though this is really a theoretical connection here, we don't really optimize this. So sorry, I didn't mean to do this. We don't really optimize this quantity. It's more of a theoretical connection. But the Jensen-Shannon divergence is not hard to optimize. You can still optimize it because it's really a KL divergence, right? It's a symmetric KL divergence term. So you can compute gradients, etc. Yeah, exactly. So you don't know the real distribution, right? So that's the reason you need to do this. So a lot of this is just an existential theoretical proof that says that if you have the optimal generator and discriminator, you are solving something that is correct, right? Yeah. So what do you mean by elbow? Um, the GAN loss is like a lower bound. So what is it, a lower bound on the divergence? I'm not exactly following. Oh, I see. So yeah, I mean, you're basically minimizing this, right? So actually minimizing, so min G max D of LGD is equivalent to actually minimizing G of like this term, which is LGD star, right? Which is nothing but minimizing G of the Jensen Shannon divergence of like PRPG, right? So this is basically the function on G, right? So this is basically the quantity, just that this cannot be done, right? Yeah, so from that perspective, yeah, I think that's right. Okay, any other questions? I think in the interest of time, I'll just move ahead. So I think this is one of the last applications, and then I'll talk about bi-level optimization very quickly and then end this part. So min-max adversarial robustness, the basic idea is that you take an image. This could also be done for text, by the way, or other things, right? So you take your data, which is xi, right, and you're adding some eta noise, right? This eta noise looks very weird, right? But for finally, once you add it, there is, I mean, you cannot really make out any difference between these two, right? It looks the same. But once you add this adversarial noise, this noise has been generated in an adversarial manner, right? So it's not random noise. If you add random noise, probably your deep model will be robust to it. But it's a very specific noise, adversarially generated. And this, once you add this to your deep model, you can actually kind of change the prediction, right? So in some sense, deep models are not robust to this, right? So this is a problem, obviously, and one way that this is solved, of course, this is not the best way, and there are issues with this, and I'll tell you what the issues are. But one way to view this is to actually formulate the problem as an adversarial, like, robust learning problem, right? So your adversarial loss essentially is, again, you're minimizing your theta. D train is the number of training examples, right? And this is a standard loss, the sum of on your training set. But now you are actually taking this max of delta, right? So you're trying to do this in a min-max manner. So you're seeing what is the maximum possible delta that you can perturb this, right? So you're perturbing your x so that your loss becomes very bad, right? And you minimize this on the worst case loss. Again, your delta x basically is like some neighborhood, right, around x. So it's a neighborhood around x, right? Um, so as long as you can define your neighborhood, you can basically still optimize this. Well, how do you optimize this? You need to do gradient descent. So you take your gradient descent like this, but you can actually compute this easily, right? Because as we have seen in convexity, that the max of a set of functions is kind of convex, right? And here you can actually you can compute the gradient of this max by taking the gradient of the delta star, where the delta star is the argmax, right? So you compute the perturbation which perturbs your loss the most, and then use that when you're computing the gradient. So one issue with this, unfortunately, is that while this becomes more robust, right, it actually turns out to affect the accuracy significantly. So there is a trade-off here, right? The more robust you make your models, you will affect prediction accuracy, and that's why this is a very open and field that people are studying extensively. That how do you actually make your make your models more robust, right? While while ensuring that you can not lose your accuracy significantly, right? So that's the goal of this entire this entire thread. Okay, so I'll cover bi-level optimization, and this will be the end. This is again a very powerful framework. MAML is one example, but broadly speaking, bi-level optimization, we didn't cover bi-level optimization, but it's a very important kind of framework of optimization. And the idea is that you want to solve problems like this, right? Where you minimize x of h of some yx, right? Where yx is equal to argmin of y g of x comma y, right? So in other words, the optimization problem is where you're minimizing over x h of argmin over y g of x comma y, right? Of course, there can be some other function of x as well, which is like r of x, right? Or maybe, to be more concrete, you could have this as a function of x additionally plus r of x, right? So essentially what it means is that there is an inner argmin over here, right? And this inner argmin is a function of x, but you need to solve this inner argmin, right? Is this problem setup clear? So this framework is actually what is known as bi-level optimization. Any questions? Okay. So where is bi-level optimization useful, right? So let's take a few examples. So one example is hyperparameter tuning, right? So imagine that so suppose you have your hyperparameter which is like lambda, right? Which is your regularization. I mean, I'm just taking one hyperparameter. By the way, like typically hyperparameter tuning is done on a validation set where you actually tune it. You tune your training, right? And then you tune your parameter lambda and see which one performs best on the validation set, right? Now, I mean, it's easy to do hyperparameter tuning if you have like one hyperparameter or like 5 hyperparameters, but imagine you have hundreds of them, right? Then you cannot really do a grid search of hyperparameters that easily and do this efficiently, right? So that's where hyperparameter tuning, bi-level optimization becomes very powerful. And the basic idea is that imagine that you are solving your so your problem there is basically to minimize lambda, right, of your validation set performance, right, of theta lambda, right? So theta lambda is your model parameter, which is a function of lambda, right? Where theta lambda is nothing but argmin of theta of my loss function theta plus lambda times some regularizer of theta, right? Now, of course, again, for simplicity, I've just assumed lambda to be a number here, but lambda could also be a vector, right? You could have like hyperparameters, which is for every coordinate, for example, right? And then doing like standard hyperparameter tuning becomes tough. Then you need to do like this more complicated hyperparameter tuning, right? So this is an example of bi-level optimization. Any questions? Another example is actually reweighting, right? So imagine that you have weights W1, W2 until Wn for your data points, right? And now I want to minimize my weight again on a validation set of theta W, right? Where theta W is nothing but argmin of theta, and you have sum of I from 1 to n, Wi, Li of theta plus some lambda times regularizer, right? So here what I'm doing is that I'm trying to reweigh my data points so that it performs well on my validation set. Now, why do I want to reweigh my data points? Reweighting becomes important if your data has noise. Imagine that your training data has noise, right? And you want to learn that which training data points I can set my weight to be 0, right? So I can ignore those data points when I'm training, right? Because if there's noise, I don't want to train on my noisy data samples, right? Another example where reweighting becomes useful is where you have like imbalance, right? So all of these are examples of bi-level optimization and things like that. So in fact, bi-level optimization is very powerful. There are other examples like, there is like network architecture smoothing, network architecture search based applications where you can pose this as bi-level optimization. You can do, like auto augment, right, and so on and so forth. So there are actually several interesting applications that are coming up now where it would require a form of bi-level optimization. Okay, so this is the bi-level optimization, right? So how do you solve bi-level optimization? So let's take the reweighting scenario, right? And over here, basically, we have the outer problem, right, where you are doing argmin over w of lv theta t star w, right? So this is a function of w, comma w, right? And the inner optimization problem is where you are solving theta star to be argmin for a given w, right? So this is the outer loop and this is the inner loop, right? And now the way you can solve this, so actually ignore lot of this because I took this from a paper. But the basic idea is that you take like one gradient step in the model parameters, right? So instead of doing this, which is this argmin over theta, similar to meta learning, you take one gradient step, right? So you take one gradient step, which is theta t plus 1 is theta t minus alpha times this, and then you substitute this theta t over here in the outer loop, right? And now because you're taking one gradient step, you can actually optimize this very easily, right? And you can then do this procedure, right? And it turns out that this actually turns out to perform very well in many applications. All right, so I think with this we can now move on to discrete optimization. But I just want to see, are there any questions on the continuous optimization part? Is line search a kind of bi-level optimization? That's a good question. I don't think line search is a bi-level optimization because you are not. I have to think more about it. I don't see the connection with bi-level optimization though for line search. I think the line search is not a bi-level optimization because in line search you want to find the optimal step size, right? So it's like a one-dimensional optimization problem where you take your gradient step, right? But it's not really a bi-level optimization. Bi-level and min-max. So it's true that both are doing it in an alternating way. But that way, I mean, alternating minimization is a very well-known technique, right? I mean, lot of flavors of deep learning today are using alternating minimization. Like joint learning is almost always alternating minimization. I mean, GANs are alternating minimization. So from that perspective, yes, bi-level also is solved in an alternating manner because you are optimizing your model parameters and you're optimizing your weights, right? But I think, I mean, I'm just saying that a lot of learning today is like alternating, right? And joint, like most of joint learning today is done in that way. Yeah. That's a good question though. Any other questions? Okay, so if not, then let us take a 5-minute break and again start at 1:37 or 1:38. And I think at this point, we'll actually start with discrete optimization. So I'll actually cover a few different applications of where discrete optimization come in, um, after the break. Yeah. Okay, so Harsha, I'll just answer your question after the break. Yeah, thanks. Okay, hey guys, can you hear me?
Yes, Professor.
Okay. So yeah, so Harsha, your question on bi-level versus meta-learning. So actually, meta-learning is a special kind of bi-level optimization because the optimization variable in meta-learning, right? Um, so for example, over here, the way we are kind of written it down, right? So if you see here, this is itself, so the inner optimization problem involves this theta prime I, theta, right? So theta is the outer variable, right? So basically meta learning, we are doing like minimum of theta of sum of I from 1 like to k tasks of this L of theta I prime theta, right? So the inner optimization problem involves theta I prime theta, where you basically want the optimal theta based on your initialization theta, right? I mean, sorry, like the inner variable, say theta i's, right? You want the best theta i's given the initialization theta, right? And theta I prime here is basically taking one gradient step of this, right? So MAML is a special case of bi-level optimization, right? But bi-level optimization is the general framework essentially of this. Does it answer your question? Okay. Um, okay, so should we continue? All right, so I'll cover a little bit now on the discrete optimization, right? I'll talk about few applications around data selection, active learning, feature selection, model compression, summarization. I'll also talk a little bit about towards the end. I'll talk about how these appear as inference in different models, right? In machine learning. So the underlying theme over here is that discrete optimization comes up in applications where we want to either select subsets of data or features or parameters, right? Or something like that, right? Or where we want to do an inference for a given task that involves essentially a combinatorial problem. So I'll skip some of this. Actually, I borrowed some slides from a previous talk that I'd given. So one of the motivating applications here is to train machine learning models on a very small subset of an entire data set, right? So that you can save on like energy and time and things like that, right? So there are a few different approaches which I'll cover at a very high level very quickly. So one is, and I think Krishadeja will be talking about this when he presents next week in more detail, right? But the basic idea is that we want to select a subset S. So you have an entire larger set of data set D, right? And we want to select a subset S so that S matches D with certain properties, right? So there are a few ways we can do this. One is gradient matching. And what we do in gradient matching is that we try to come up with a set of weights and a subset S so that we can try to minimize basically a weighted sum of the gradients, right? So this is Li minus sum of I in V of gradients of Li theta, right? So the idea is that can we come up with a weighted subset so that the sum of the weighted subset on the subset is equivalent to the full gradient, right? So we are approximating the gradient with a weighted subset on a very small set S. So that's the basic intuition of gradient matching. And another scenario, basically another way of doing this is through bi-level optimization, but a discrete bi-level optimization, right? So discrete bi-level optimization is where you want to find a set S which minimizes the validation set performance, right? And here you have theta, which is a function of S, right? Where theta S is itself an argmin over theta over sum of I in S, Li of theta, right? So essentially, this problem is a bi-level problem because given a subset S, we are trying to achieve the best parameters where you train this on a subset S, right? And we want to in turn have the smallest validation loss, right? So this is a paper called Glister, and then there's one more called Craig. So Craig actually is very similar to this gradient matching, but it does it in a slightly different way, right? So this is the basic idea of subset selection over here, that we want to obtain subsets of data where we can actually match this to an entire set. And in fact, this is actually work done by Krishateja, who's actually attending the class. So he'll be covering some of this work, I think, in his presentation next week. This is some empirical results, but I'll actually skip this in the interest of time. The other application, so the first application was selecting data subsets with the goal of training efficiency, right? So if you see, for example, the results over here, then you can achieve with very small, so the green here is the relative test error, right? So you can achieve almost 3x to 5x speed up with basically like around 2%, between 1 to 2% loss in accuracy, right? And this is across several data sets like CIFAR10, CIFAR100, ImageNet. So essentially what it means is that we can considerably speed up deep learning training procedures today, and also actually make them significantly more energy efficient, while not losing too much on accuracy, right? So this is some of the results that GradMatch obtains. In fact, I'll actually show this. So this is a CIFAR10 convergence plot, right? So you see CIFAR10 actually, if you use the full training, it converges in around 4.5 hours, right, to around 94% accuracy. But using Glister, basically, which is the bi-level optimization approach, right? We can achieve this within like just less than an hour, right? So we are able to significantly speed up deep learning, which kind of consequently will imply lesser energy consumption and lesser cost involved in training deep models, etc., right? So there are a lot of nice properties with doing something like this. Furthermore, you'd also want to do something like this when you do hyperparameter tuning, right? Because if you're tuning hyperparameters and running this deep learning multiple times, you want to do this on a subset of data, right? So yeah, so this is one of the efforts which like I'm particularly very interested in my group. So again, like if any of you are interested in this, let me know also. So the second problem is related to active learning, right? So the active learning setting is that we want to actually label data sets, but we want to significantly save on labeling costs, right? So the goal here is, can we label a fraction of the data set, like say 10% or 20% of the data set, right, while achieving a certain accuracy that we care about, right? So suppose, for example, on CIFAR10, can we achieve 90% accuracy with just like 10% of the CIFAR10 labeled, right? Or maybe 20% of CIFAR10 labeled. So that's what active learning algorithms try to do. And it turns out that there is a significant gain that active learning can achieve on top of random sampling, right? Which is good news. So there have been a lot of approaches to do diversified active learning, right? So the basic idea is that you want to somehow combine uncertainty and diversity. And I'll actually look at two techniques. One was actually work done by us almost 6 years back. In 2015, this ICML paper, and there's been actually several papers in between, even recently a 2020 paper in ICLR by Ash et al., right? So the basic idea remains the same, that you want to somehow combine diversity and uncertainty in a principled way, right? So the first approach, right, which is a very early work in 2015, also a paper in 2017 by us, 2019, where we basically can do active learning in a filtered manner, right? So the idea is that you kind of filter out uncertainty. Okay, so actually one thing I should mention over here that I didn't mention, that all of these are discrete optimization problems, right? So this entire subset selection is posed as a discrete optimization problem, and in fact it turns out that for all three of these we can actually connect it back to submodularity. Right. So we showed, for example, that Glister actually involves solving a submodular maximization problem, right, for several loss functions. So for several loss functions L, you actually do a submodular problem here. Craig was actually worked by Behran et al. In 2000, I think it's a 2020 ICML paper. So Craig is another approach which is similar to this, but it actually relaxes this to a facilitation problem and it connects it to submodularity, right? So the basic point here in these discrete problems is that we are starting with problems or formulations that make sense, but it turns out that we can actually connect them back to submodularity, right? So the same we also do in active learning. So in the case of active learning, we first do an uncertainty filtering in this algorithm, right? And then once we filter out the uncertain examples, then we actually formulate this as a submodular max problem, right? So this is a submodular maximization problem. And if you recall, we actually studied submodular maximization, in I think the last to last lecture, right? So essentially, we would be using the algorithms from there to do this. Okay, so this strategy is called filtered active submodular selection. And then it turns out that there was work in 2020 where they actually came up with a very interesting approach, right? So the idea is that if you pick up a set of diverse gradients, right? So if you pick up a set of diverse gradients, then essentially what goes on is that you can do, in some sense, you are naturally doing kind of uncertainty and diversity together, right? Because when you pick up diverse gradients, you're also picking up gradients with a higher magnitude, and correspondingly those points will be more uncertain, right? So there's been actually some interesting work where you can define like diversity functions on the gradients of the loss function on the given theta, right? And this was what the badge paper is basically. So given this, actually, we can now use even other submodular functions potentially depending on the gradients. And I think one interesting direction to pursue for future is to study the effect of like submodular gradients, right? So how do submodular gradients perform with active learning, right? So that's an interesting thing. Okay, so I'll talk about one more application. This is still work in progress. So this is actually been looked at by Suraj. I think Suraj might present some of this next time, like in his course presentation. But I'll give you the high level idea. So imagine that we are doing active learning, but now in active learning, right? So this is like, so I have a small labeled set over here, L. I have my unlabeled pool, right? But my unlabeled set comprises of say 3 classes, right? So the first class basically is something like this, right? And the second class is something like this, or say I have 4 classes, right? And the third class is something like this, right? So this is, so sorry. So say this is class 1, right? I forgot the colors, but say this is class 2, right? And this is class 3. right? And this small portion over here is class 4. Right, so as you can see, class 3 and class 4 are underrepresented here in my unlabeled set, right? So the question is that how do I perform targeted active learning, right? So that when I'm sampling data points, I can ensure I sample a good representation of class 4 points, right? Because imagine class 4 is is underrepresented, but it is also significantly important because it comprises of rare events, but those rare events could be very costly. So imagine, for example, that class 4 comprises of, or it could be slice 4, which comprises of scenarios where there are people in highways in the dark, right, for a self-driving car application. So this slice may not happen very often, right, but it's a super critical slice because I don't want to have, I mean, that is a point where I can actually have more accidents, right, at night because of low visibility. So I want to make sure that my model can perform really well even on these slices. So the question is that how can I apply targets or queries to my active learning? Right, so this is something that we have been investigating, where we can actually do something like a submodular mutual information function, right, where we try to select basically a subset A over here, which is a subset of labels to obtain, right, in my active learning. So in my active learning, recall that I'm trying to sample data points every time in a batch, right? So how do I sample data points through this set A so that it is similar to this targeted set T, right? And my target could be this class, which is very rare. Okay, and it turns out that actually these submodular mutual information functions are very powerful over here. They perform much better than existing active learning algorithms in obtaining class 4 examples, right? So this is the basic idea. Any questions on this so far? Any questions on the setting, or are things clear? Okay. Okay. All right. So we'll switch gears a little bit now. So I covered active learning. I covered feature selection. Right. A lot of submodularity is useful over here. There is another set of applications which is related to features like obtaining or a kind of eliciting features, right, or feature selection. So kind of motivating applications here are, imagine that you want to elicit features for a test time, right? And oftentimes each feature has a cost. So for example, obtaining lab tests could be expensive, right? So how do I do feature selection in a kind of smart manner where I can select subset of features to obtain for a given data instance, right? And these features could also be dependent on the individual person at hand as well, right? So they could be both dependent on the person as well as the scenario that we have. So we want to come up with these rich feature selection approaches. The second application of feature selection is that we want to do like parameter compression, right? So this is essentially, this application is like model compression or parameter reduction. So how do I compress my models so I can run them on low resource edge devices, right? This would be important to run on edge, for example, for privacy constraints, because I don't want to send my data from my home. I don't want to send it to a cloud, right? I want to ensure that the data that I have at home is basically stays on the edge device only, right? Similarly, there's low latency, bandwidth cost, etc., right? So there are a couple of approaches for feature selection, and the basic premise here is that you can do mutual information based feature selection. So the idea is that we have a set of features A, right? So I think this should be A actually over here. So this is A, right? And XA is a set of features. So how do I select a subset A of features which maximizes the mutual information between my class and my set of features, right? So here y is the class variable, and xa is a subset of features I'm selecting. So how do I maximize this feature selection, this feature, right? It turns out that this function is not always submodular, but it is actually monotone, right? However, it is submodular if the xi's are all conditionally independent given y. Okay, so if you have like the naive Bayes assumption, right? So this is the naive Bayes assumption, right? Then it is actually submodular. Okay. But it turns out that the naive Bayes assumption can be very limiting, right? Fortunately, it actually turns out to be a difference of submodular functions. So this is something we showed in our 2012 paper. But the problem with this entire framework is that actually estimating the mutual information can be difficult, right? Particularly for large feature sets. So there has been a nice chain of work on actually kind of estimating this using basically kind of breaking it down into relevance and redundancy, right? So it's like a proxy function where you can write down this mutual information in this way, right? So the first is like just the sum of I in A, the mutual information in xi comma y, and the second is like the joint mutual information between xi comma xj, right? So this thing is the this is called MRMR essentially. Okay. And there are actually several other formulations like this, and this turns out to be still submodular, right? So that from that perspective, this is a kind of an interesting formulation. And then we did some work to extend this to cost-aware feature selection, and basically the intuition was the medical application I told you about, right? So where you have your data set, and imagine that you have clusters of data of like similar age groups of people, right? And based on the cluster, we want to figure out which test to order. So for example, there could be fMRI, there could be a lab test, there could be X-ray, there could be different tests that could be ordered for different groups of people, and maybe given the age group, there might be higher or lower chances of certain diseases, and certain tests might be good enough. Maybe a blood test is good enough there, right? Or maybe just the symptoms are probably good enough there. We don't have to actually order tests. So this is what a doctor does all the time. And the question is, how do we do this in a feature selection approach? So it turns out you can actually extend this kind of feature selection now into a clustered approach, right? Where you cluster the most important features for every cluster, or like every demography or age group, etc. And then basically figure out the feature selection at that level, right? So yeah, so all right. So now I'll very briefly talk about model compression. There's been a lot of work here in this thread. I don't have time to cover it in a lot of detail, right? But the basic idea is that people have tried to apply ideas like core sets, right, to try to compress models. So basically, given deep neural network, something like this, we can actually prune these, right, by using the activations, and then we can actually kind of get a subset of layers over here, right? But the basic idea is that after doing the compression, we want to be able to still, be very close to this, right? So that's why we have this kind of decompression matrix, right? So we can compress this, but once we decompress, it is somehow very close to this original feature representation. I mean the original network. Yeah, do I?
Is this the same as the idea of or the concept of ResNet, or is
no, this
ResNet
is not.
something different?
So this is actually to compress a model by having a much smaller set of weights, right? So that the performance of the model is very similar.
Oh, okay, good. Okay.
Right. So the question here is that you are given a deep neural network which is probably already trained. You don't care about training time. but you want to somehow reduce the layers. You want to remove like certain activations, right? So that you can basically get a smaller model, right? So quantization and weight binning are different ways of doing this. That is to reduce the model size, but oftentimes when you do quantization or weight binning, you are still retaining the same number of parameters, right? All you're doing is you're just quantizing it into like say 0 1s, like binary neural networks, or you are quantizing it into like 4 bits or something, which also is very powerful. But I think what the other aspects of compression try to do is to actually try to remove certain layers, for example, right? So that you can do the forward passes much faster. So there have been multiple papers in this. Again, I won't be going over this. I mean, this itself could be a lecture to kind of survey the entire space here, right? But I think that this is another interesting and yet very important application of discrete optimization here. And I think again, this is an area I'm very interested in as well. Any questions? Okay, so I think this is the end of the lecture. I'll talk about one last application, which is like inference in models, like say probabilistic graphical models, right? And one particular example is basically a application like image segmentation, right? So imagine that you have your model something like this, right? So this model is known as Markov random field, right? And I'm sure many of you have taken Weaver's course or are taking Weaver's course on probabilistic graphical models. I'm not an expert in PGMs at all, right? But basically, this problem, the problem here in inference, right, is you are given a parameterized model, right? And now given basically your image features, you want to come up with your y, right, where your y is your label, which is essentially the segmentation of the image, right? So the idea is that given an image, you have like a certain person in this image, right, and this is the foreground and the rest of it is background, right? So how do you segment this image? So this involves actually a discrete optimization problem, because each of your picks, your output here could be either 0 or 1, right, whether it belongs to the foreground or the background, right? So your y here is nothing but in 0 1 raised to n, right? And you can actually solve this using a Markov random field. So the inference step basically is something like where you're minimizing an energy function of E of x, which is essentially something like this, where again I don't remember exactly, but I think it's something like this. So you have like some pairwise potentials, right, plus some maybe there is no. So I'll just call this like yi over here, right? And then there is the yj, right? So this is the pairwise potential over here, right? And under certain conditions, this is submodular, right? And this energy minimization actually turns out to be a submodular minimization problem. And there's been a lot of very, very nice seminal work in the 2000s and the 2010s by Yuri Boykov and many others actually. I think Kolmogorov also, Vladimir Kolmogorov. So a lot of them, they did this nice work where they did like submodular minimization and showed a lot of theory of submodular minimization. But this is another application where submodular comes in, but from a minimization perspective, right? Yeah, so there are actually several others. In the interest of time, I won't go over them. There are things like, reducing the complexity of a data set, right? So for speech recognition, for example, creating a low complexity data set for kind of prototyping, right? This turns out to be a form of submodular minimization. Then there is an image correspondence application where you want to kind of compute correspondences between pixels, and you can actually kind of employ certain cooperative kind of cooperative kind of objective function there. So right, so that groups of pixels that are together can be matched into groups of pixels that are together, right? And we call this cooperative matching. So this is an example of image correspondence problem that has submodular minimization, right? So there are actually many applications of submodular minimization as well in machine learning that have been growing with importance, right? But I think in the interest of time and also to make sure that I give you guys kind of enough time to ask questions, we'll end over here. And yeah, so the floor is open. So let me know, do you have any questions on anything that was covered today or this course? Anything that like any feedback on the course that you'd like me to try out for next time? Yeah. Any comments, any suggestions, any questions?
So regarding,
Yeah,
okay.
Oh, yeah, I just wanted to ask, is that a second homework almost available? Or?
Yeah, actually, I was going to post it last week, but I fell sick, and then my wife also fell sick because of the vaccine. We took the vaccine, and I ended up, kind of losing a couple of days in getting things done. But the homework is almost ready, so I'll probably sit after the class and try to get it done by tonight. So, as I said, the second homework is optional. It's a very short homework with 2 questions, right? And I mean, I think for those of you who are interested in just learning more, I would encourage you to try out the homework. But it's optional. So either we will have the first homework, or basically I can also use both homeworks. So yeah, so that's the thing. Yeah, but I will be posting the homework today evening. Any other questions? Yes, you are.
Regarding the lecture today, you mentioned a couple of methods for problems where you have a small data set.
Mm-hmm.
One of them is the I think MAML or meta.
You mean for few shot learning?
The meta. I can't remember the other.
Yeah, meta learning.
Yeah, the meta learning. So for that in particular, if you have a data set with like few hundred pictures of, let's say, eye tumors, is this a good model to be able to predict a certain tumor, like a carcinogenic tumor over regular tumors?
Yes. So the whole goal of something like meta learning and MAML is essentially in this few shot learning scenario, right? So the few shot learning scenario, you have very few images, and the idea is that you have a slightly bigger meta training data set of similar kinds of images or similar tasks, right? So can we use these similar tasks so that when I'm given a new task, I can actually apply this, right? So imagine, like take CIFAR 10 as an example, right? Imagine your tasks, you have multiple tasks from CIFAR 10, which are like say cat versus dog classification, right? Or you have like a cat versus truck classification, right? Or truck versus dog classification. So you have many tasks like this. And now at meta test time, you have very few images of say sheep, right? To detect sheep versus dogs, or like sheep versus non-sheep, right? So how do you so you can basically apply this now in your meta test time to to work on these very few examples. Like suppose you have 5 examples of sheep and 5 examples of non-sheep, right? So you're doing like a basically 5 shot learning, and in this 5 shot learning, you want to with 5 examples you want to be able to predict this with good accuracy, right? So if you just do supervised learning here, it's not going to work, right? So the whole idea of meta learning is you can use this past data set, right? So that you can learn a good initialization, right? And hopefully this good initialization can then be fine-tuned on your sheep data set so that you can create a classifier now to detect sheep versus no sheep. Does it answer your question?
Yes, thank you.
Yeah. Any other questions? Yeah. So yeah, thanks for the reminder actually. So I will actually post those demos. So I don't have the demos. So I just have the demos for the conjugate gradient and the Barzelia-Borvin. But let me post that immediately after the class. So I'll do that immediately after. So I've been forgetting about it actually. So yeah, thanks for the reminder. Yeah. Any other questions? Since I annotated these notes, I have actually posted notes on the GitHub, but now I will also post the annotations actually. Okay. So yeah, so let me know if you have any other questions anytime, particularly if you have any questions on the um, on the so would you provide solutions to assignment? Yeah. So I will be providing the solutions to the assignment one, and I'll post them this coming week. I see. Yeah. So sure. Yeah. Thanks for the feedback, Justin. I think that the idea was to use the data set that was provided, but probably what you are saying is to give like to implement the functions and give like a test environment where everyone can implement it in the same way, right? So I think I'll do this for the next version. Yeah, thanks. Any other questions, suggestions? Okay. So again, thanks so much. I really enjoyed putting together this course. This is the second time I taught this course. Like the first time was last year, but I think the course was slightly different. It was my first time that I taught it last time. In fact, it was the first time I taught any course last time, so it was a bit rough. But I tried to polish it a little bit more this time. But I think this course is evolving over time. The other thing is that because it was a PhD level course only, it was a little bit more advanced than what I did last time. So hopefully, I'm hoping that it was useful to you guys, and I'm hoping it'll be useful for your research also moving forward. So yeah, do let me know. Kind of continue giving your feedback as well on the course. And let me know if you have any questions on any of the material. The YouTube lectures will be there online basically throughout. So you know, you can basically view the lectures afterwards as well. So it won't be going anywhere. And yeah, I think it was great having you guys. Hopefully you kind of learned something here. So sounds good. So like as I said, the final 3 weeks would be just course presentations, and then we will basically be ending the course. Yeah. All right. Take care. I think we can end early today. So have a good weekend, and I will keep posting. So hopefully you will see a message from me today or tomorrow on the homework 2, which is optional, and the schedule is already out for the presentation. So we will follow the schedule next week. So basically next week we have, I think, Suraj, Parth, Krishna Teja, and Nathan. So they'll be doing first, and then I think we'll be following with the other students the rest of the 2 weeks. Yeah. Yeah, exactly. So yeah, thanks. I will be keeping the recording on YouTube. Yeah. Okay. Yeah. Thanks for your feedback and your encouraging messages here. All right, guys. Take care. Take care. Have a good weekend. Stay safe. I hope most of you have taken your vaccinations. If not, please do take your vaccinations, and generally stay safe. Yeah. Yeah. Thanks.